Look up at the night sky. What do you see? A velvet black canvas sprinkled with the brilliant shimmering light of countless stars. You might see the faint, milky smudge of a distant galaxy, a city of 100 billion suns, its light having traveled for millions of years to reach your eyes. It all seems so vast, so complete. But what if I told you that everything you see, every star, every galaxy, every planet, every speck of dust, is just the froth on the surface of a much deeper, unseen ocean? What if the universe we perceive is merely a tiny fraction of what is truly out there? This is the starting point of one of the greatest mysteries in all of science. There is a ghost in the cosmos, an invisible presence that permeates all of space, its influence felt but its form unseen. It doesn't shine, it doesn't reflect light, it doesn't seem to interact with any of the matter we are familiar with. Yet, its gravitational pull is immense, a silent conductor orchestrating the grand cosmic ballet. This mysterious substance, this cosmic phantom, has a name: dark matter. It is the missing 85% of the universe, a profound puzzle that challenges the very foundations of our understanding of reality. Imagine you are in a vast, dark room. You can't see the walls or the furniture, but you can feel a gentle breeze, a current that guides your movement. The first clues came not from what we could see, but from what we could measure. In the 1930s, an astronomer named Fritz Zwicky was studying the Coma cluster. He measured how fast these galaxies were moving relative to one another. What he found was astonishing. The galaxies were moving so quickly, so erratically that the combined gravity of all the visible stars within them shouldn't have been nearly enough to hold the cluster together. By all rights, the cluster should have flown apart millions of years ago, its constituent galaxies scattering into the void. Zwicky hypothesized that there must be some other unseen material present, something he called Dunkel Materie, or dark matter. This invisible mass, he proposed, was providing the extra gravitational glue needed to keep the Coma cluster intact. At the time, his ideas were largely dismissed. The concept of a universe filled with matter we couldn't see seemed too radical, too outlandish. It was easier to believe that his measurements were simply wrong, or that there was some other, more conventional explanation for the rapid motion of the galaxies. The mystery, for a time, was put back on the shelf, an oddity waiting for its moment to re-emerge. Decades later, the mystery deepened. The problem wasn't just confined to clusters of galaxies, it appeared within individual galaxies themselves. Think about our own solar system. The planets closest to the Sun, like Mercury and Venus, orbit much faster than the planets further out, like Neptune. The definitive evidence for this galactic anomaly came in the 1970s, thanks to the pioneering work of astronomer Vera Rubin. Working with her colleague Kent Ford, Rubin conducted meticulous observations of the Andromeda galaxy. Using a powerful spectrograph, she was able to measure the orbital speeds of stars at various distances from the galactic center with unprecedented accuracy. The data she collected was unambiguous and startling. The galaxy's rotation curve, a plot of orbital speed versus distance, was almost completely flat. The stars at the edge were not slowing down. They were racing along at a constant high velocity. This observation was a direct contradiction of everything we thought we knew about gravity and the distribution of matter in galaxies. The only way to explain their incredible speed was if the galaxy contained a huge amount of unseen mass extending far beyond the visible disk of stars. This mass would have to be distributed in a vast spherical halo, enveloping the entire galaxy. Rubin and Ford didn't stop with Andromeda. They went on to study dozens of other spiral galaxies, and everywhere they looked, they found the same thing. From small galaxies to large ones, the story was consistent. Their rotation curves were flat. This wasn't an isolated fluke or a measurement error, it was a universal property of galaxies. The implication was profound. The luminous matter we see, the brilliant stars that make up the beautiful spiral arms, is just a small component, embedded within a much larger, much more massive halo of dark matter. The visible galaxy is like a tiny boat floating on a vast, dark ocean. The work of Vera Rubin fundamentally changed our picture of the cosmos. It transformed dark matter from a fringe, speculative idea into a central pillar of modern cosmology. Her careful, systematic observations provided irrefutable evidence that the universe was hiding a monumental secret. So just how much of this invisible stuff is there? The answer, derived from a multitude of different observations, is staggering. From the rotation of galaxies, the motion of galaxies within clusters, and the way light from distant objects is bent by gravity, gravitational lensing, a consistent picture emerges. The ordinary matter that we are made of, The stuff of atoms, protons, and electrons makes up less than 5% of the total. It is a cosmic rounding error. Everything we see and interact with is just a sliver of reality. The rest of the universe is divided into two enigmatic components. About 27% of the cosmos is thought to be dark matter. This is the stuff that provides the extra gravitational pull, holding galaxies and galaxy clusters together. The remaining 68%, an even greater mystery, is something called dark energy. 68% dark energy, 27% dark matter, 5% normal matter, but it is the 27% share belonging to dark matter that dominates the mass of the universe, outweighing all the visible stars and gas by a factor of more than 5 to 1. This means that for every gram of ordinary matter, every star, planet, and person, there are more than 5 grams of dark matter lurking somewhere in the cosmos. Think about that for a moment. The universe is not what it seems. We are living in a cosmos dominated by a substance we cannot see, cannot detect directly, and do not understand. The universe we have studied for centuries, mapped by our telescopes, is merely the visible tip of a colossal cosmic iceberg. Once astronomers were convinced that dark matter was real, the next logical question was, what is it? The simplest explanation would be if it were made of the same stuff we are: protons, neutrons, electrons, just in a form that is difficult to see. Maybe it was composed of massive, compact objects floating through the halos of galaxies. This category of potential candidates was given the acronym MACHOs, Massive Astrophysical Compact Halo Objects. Candidates included brown dwarfs, failed stars not massive enough to ignite nuclear fusion, and rogue planets ejected from their solar systems. These objects would be incredibly faint, practically invisible over interstellar distances. They wouldn't shine like stars, but they'd still have mass and exert gravity. For a time, this seemed like a plausible, almost elegant solution. It didn't require inventing any new, exotic physics. Astronomers searched for machos by watching for rare microlensing events, one passing in front of a distant star and briefly magnifying its light. After years of searching, there were far too few microlensing events to explain the dark matter implied by galaxy rotation curves. Machos exist, rogue planets and brown dwarfs, but are far too rare to solve the mystery. The universe's ghost was more elusive and exotic than dim celestial bodies. The answer had to lie beyond familiar matter. This led physicists to a much more radical conclusion. Dark matter must be made of something entirely new. It cannot be composed of the familiar particles described by the standard model of particle physics. It must be a new type of subatomic particle, forged in the primordial soup of the Big Bang, and largely aloof from ordinary matter ever since. This realization opened up a new frontier, sparking a global search for a particle that interacts almost only through gravity. With machos largely ruled out, the focus shifted to the world of the very small, hypothetical subatomic particles. The leading candidates for dark matter fall under the umbrella of WIMPs. WIMPs stands for Weakly Interacting Massive Particles. These would be particles that are quite heavy, perhaps many times more massive than a proton. They interact with other matter only through the weak nuclear force, or gravity. This weak interaction is key. It explains why they are so difficult to detect. A WIMP could pass straight through you, the Earth, and the Sun without ever bumping into a single atom. WIMPs are predicted by some extensions of the standard model, such as supersymmetry. Those theories propose a heavier superpartner for every known particle. The lightest superpartner would be stable and produced in vast quantities in the early universe. If such a particle existed, it would be massive. It wouldn't interact with light. It would interact only weakly with ordinary matter. It seems like a perfect fit, a theoretical puzzle piece waiting to be found, but WIMPs aren't the only option. Another candidate is the axion. Axions are incredibly light, perhaps billions of times less massive than an electron. They were proposed to solve a problem with the strong nuclear force. If they exist, they were produced in colossal numbers in the Big Bang, and now form a vast cold sea bathing the cosmos. Unlike a WIMP single particle, a galaxy's halo could be a dense, coherent wave of trillions upon trillions of ultralight axions. The search for dark matter is a tale of two extremes. On one hand, experiments hunting a rare faint signal from a single heavy WIMP bumping a nucleus in a detector deep underground. On the other hand, experiments sensing faint wave-like oscillations of a vast axion field. Both are tantalizing, and both push technology to its limits. The true identity of dark matter remains a mystery, but these candidates give concrete targets in our ongoing cosmic ghost hunt. The fundamental challenge in detecting dark matter is that it is, by its very nature, antisocial. It does not want to be found. Dark matter particles, whether they are WIMPs or axions, are thought to pass through ordinary matter almost as if it weren't there at all. Billions stream through your body every single second yet leave no trace. They don't emit light, absorb light, or reflect light. That's why our telescopes are blind to them. They also don't interact through the strong nuclear force or the electromagnetic force. Those forces govern nearly all our interactions. To detect a WIMP, scientists build incredibly sensitive experiments and place them in the quietest places on Earth. That means going deep underground into old mines or beneath mountains. The rock above acts as a shield, blocking the constant rain of cosmic rays and other background radiation from space, which would otherwise flood detectors with false signals. Down in these subterranean labs, detectors are filled with materials like liquid xenon or supercooled germanium crystals, hoping to catch the 1 in a trillion event of a dark matter particle hitting a nucleus. If a WIMP strikes a nucleus, it should cause a tiny recoil like a billiard ball collision on a subatomic scale. The recoil would produce a minuscule flash of light or a tiny vibration, which highly sensitive sensors are designed to pick up. The signal is incredibly faint, at the edge of what's technologically possible. For decades, these experiments have run, getting larger and more sensitive each year. They've found nothing so far, which lets scientists rule out some types of WIMPs, but a definitive detection remains elusive. Axion searches need a different approach. If axions are dark matter in a very strong magnetic field, they can occasionally convert into a photon. Axion experiments look like high-tech radio receivers. They use powerful magnets and sensitive cavities to listen for the faint microwave signature of axion conversion. Like WIMP searches, these efforts push technological limits, straining to hear the faintest whisper from the dark sector. The hunt is hard, but the prize is a new understanding of reality. Solving the mystery of dark matter is about much more than just identifying a new particle. It is fundamental to our understanding of how the universe itself came to be. Cosmological simulations show that without dark matter, the universe as we know it simply would not exist. The ordinary matter that emerged from the Big Bang was too hot and too evenly distributed to clump together on its own. Dark matter, however, was different. It could begin clumping almost immediately after the Big Bang, drawn together by its own gravity. It formed vast, invisible halos, deep gravity wells across the cosmos. Dark matter acted as a cosmic scaffold, the gravitational framework for the visible universe. Without this invisible scaffold, there would be no galaxies. Without galaxies, there would be no stars, and without stars, there would be no heavy elements forged in their nuclear furnaces. No carbon, no oxygen, no iron. There would be no planets, and certainly no life. Dark matter appears to be a prerequisite for our own existence. Understanding its nature is essential to completing the story of cosmic creation, from the first moments after the Big Bang, to the emergence of planets, to the formation of stars, and ultimately, to us. It is the invisible architect of our cosmic home. We stand at a remarkable moment in the history of science. For centuries we have explored the universe by studying light, but we now know that this has given us a view of only a tiny fraction of what is actually out there. The discovery of dark matter has been a humbling revelation, showing us that the cosmos is far grander and more mysterious than we ever imagined. The quest to identify this substance is one of the most exciting and challenging endeavors in modern physics. The discovery of the dark matter particle would be a watershed moment, as revolutionary as the discovery of the electron or the splitting of the atom. It would not only confirm the existence of matter beyond the standard model, but would also open up a window into a completely new dark sector of the universe, with its own particles and perhaps even its own forces. It would be the first tangible piece of a hidden reality that has coexisted with our own for 13.8 billion years. Silently shaping the destiny of the cosmos without our knowledge. The implications for physics, cosmology, and philosophy would be profound. What new physics will we uncover? Will the dark matter particle be the WIMP predicted by supersymmetry, finally giving us evidence for this elegant but unproven theory? Or will it be the ultralight axion, revealing a deep connection between cosmology and the esoteric rules of the quantum world? Or could it be something else entirely? Something so strange and unexpected that no one has even thought of it yet. The answer, whatever it may be, is waiting for us, hidden in the faint signals of underground detectors or the subtle whispers from galactic halos. The journey to understand dark matter is a testament to the power of the scientific method, the ability to infer the presence of the unseen from its subtle effects on the scene. It is a story that began with a puzzling observation about spinning galaxies and has grown into a global quest to map the invisible universe. Unmasking the cosmic ghost will not be the end of the story, but the beginning of a new chapter. It will provide us with a more complete, more accurate picture of the cosmos, reminding us that even after centuries of discovery, the universe still retains its profound ability to surprise and inspire us.